Hello and good day to all. Welcome and thank you for your time to attend the Olympus webinar. Today's webinar will be on how we can make use of a non-destructive technique, NDT, called eddy current testing for typical inspections in the oil and gas industry related to weld and tubes. So please take note that this webinar will be recorded and the recording link will be sent to you after the webinar session for future reference. So by default, your microphone will be set to mute. But if you have any questions, please type it in and we can answer them at the end of the presentation. This will be the agenda for today. We will have a short introduction on our speakers, followed by well inspection application, then tube testing application, a summary, and finally, if time permits, a short Q&A session. Okay, so today's speakers will be Franco, a senior product specialist. Franco brings with him years of experience in NDT as an inspector, especially in the aerospace, and joins Olympus providing application support and equipment training. The second speaker will be Joshua. Joshua also started off as an inspector in the aerospace industry and now joins Olympus providing sales and technical support. Together, we hope to provide an informative webinar that will benefit inspection and maintenance activities. So the first part will be on well inspection application. For brief information, okay, so brief information, wells are common and almost found everywhere. You see wells on pipes, on refinery structures, on offshore structures, on pressure vessels and various other places. Wells are very important because if they are born between parts. As such, defects such as cracks will go unchecked, will cause the wells to fail, and may lead to catastrophic consequences. This picture itself that you see shows typical cracks that can occur on wells. So before we proceed, we have a poll question for you. Once the poll question is up, you have 20 seconds to answer. And then after that, we'll proceed on to the next slide. Okay. Right. We thank you for your participation in the poll questions. So generally, the wells that we see every day, these are generally carbon steel wells. And the globally preferred method to inspect them is by using either the magnetic particle test or the penetrant testing. These tests allow the inspector to detect any surface breaking defects. All right, apologies for the slight hiccup. All right, so back to the slide. Magnetic particle testing involves using chemicals that contain small magnetic particles, either fluorescent or colored, as well as using a magnetic yoke. The magnetic particles are dispensed by means of aerosol can in between the legs of the yoke while the part is being magnetized. Presence of defect will distort the magnetic flux in the material and cause magnetic flux leakage around the floor. This flux leakage can then be displayed when the magnetic particles accumulate and build up around it. Thus, defects such as a crack is indicated as a line of magnetic particles on the surface. For penetrant testing itself, penetrant testing involves using chemicals such as a cleaner, penetrant, and developer for the test. Once the penetrant is applied, there is a duration of time required for the penetrant to be allowed to seep into the defects by means of capillary action. After that, the developer is applied to draw out the penetrant in the crack and produce a surface indication. However, what is seldom mentioned, though significant, however, is the amount of time and materials required for the inspection. We all know in the industry that time equates to money. The lesser the turnaround time, the faster that a critical part needs to be put back in service. Surface preparation is a painstaking process, but is crucial for both magnetic particles and penetrant testing. Paint and surface coatings must be removed for access to the metal itself. And in order to remove the paint or coating, strong chemical products must be employed. Additionally, the paint and coating have to be reapplied once the job has been carried out. So improper application will lead to the metal being exposed to the environment, and reaction with the strong cleaning chemicals may result in corrosion also. As the global trend is to employ more environmentally friendly processes, the use of those chemicals raises concerns across industries. Magnetic particle and penetrant testing are not easy to employ on rope access applications, and usually scaffolding must be employed frequently. As time is always the essence, thus it is not ideal to get delayed by the environment. Both techniques are difficult to perform outdoors when the weather conditions are not suitable. For example, if it's raining or there's thunderstorm, you can't use both magnetic particles or the penetrant testing. So one of the limiting factors to note about magnetic particle testing also is that it can only be applied on ferromagnetic materials, that is like steel or iron content materials. Thus, if the part is made up of, for example, zinc, then magnetic particle testing cannot be used. If we were to know how deep the defect is from the surface, it is also easier to decide on how serious it is and what repair or replace procedures to take. However, both magnetic particle testing and penetrant testing will not be able to provide any information on the depth of the defect. Thus, we introduced eddy current testing on welds. Eddy current testing uses electromagnetism principles for flaw detection in conductive materials. Basic instruments are just the eddy current instrument and probe. A reference block is also used for calibration and verification. Eddy current testing is a reliable, quick, and inexpensive way to carry out well inspection. The eddy current testing instrument developed by Olympus is the Nortec 600. It is widely used in the aerospace industry. This field-proven and code-compliant instrument is portable and lightweight, yet rugged and durable, making it suitable for performing well inspection in extreme environments. The instrument also features an inspection-ready well setup that helps simplify instrument preparation and calibration. The well probes are designed to be hard-wearing and can handle the rough well surface while still detecting faults in the well. Thus, the advantages of eddy current testing are that there are no consumables used, in which the accumulated cost can sometimes be overlooked. Minimal surface preparation and ability to test areas with poor access. Next, we shall take a look at some videos by Franco to show how easy it is to do setup for well inspection. So Franco, over to you.
Thanks, Joshua. So as mentioned by Joshua, I'll be showing you some videos on how to set up the well probe with the use of our Nortec 600. Okay, so this presentation, I'll be using the Nortec 600 with the weld kit. So our weld kit comes with the weld probe, paint thickness probe, reference standard with shims, and a weld sample. Okay, so this presentation consists of 3 parts. So first part will be setting up the weld probe. Second part will be scanning the weld sample and improving the setup. Okay, and then third will be setting up the paint thickness probe. Okay. During this presentation, I will be predominantly use some key features of the Nortec 600, such as application selection, where you can find the list of common eddy current applications in the industry. Okay, so you will also be able to change the parameters while the display is under freeze mode. You can also show multiple displays where you can include other display with the impedance plane as well. And then using the dual frequency, where you can use 2 frequency settings at the same time. And one would be also on the full display mode, where you can see the display in full. Okay, so let's start with the first part, which is the setting up the weld probe. Okay, so as mentioned earlier, so once you turn on your equipment, you have the application selection. For here, we select weld. Okay, and then change your vertical position so that it will be at the center. After which you can turn off the grid or change it to fine, which is applicable to you. And then now we can scan the 1 mm depth notch. Okay. So once scanned, you can press freeze. And then you can change the angle, rotate it until the display is going upwards. Okay. You can change also your vertical gain, if you wish so that the notch will, the display will reach at least 80% full screen height. Okay, so now you can try scanning all of the 3 notches of the standard. Okay, so that would be the result. Rotate your standard 90 degrees. And again, scan the 3 notches. Okay, so this will help you establish whether your defect is longitudinal or axial. Okay, so you can change also display. You can add sweep, or you can use both sweep and impedance, okay, as I'm showing it now. So you can increase your sweep time, so the line will go slowly on the display. Okay, then press your full for full display mode. Then scan your 3 notches again. So this will represent our longitudinal cracks. And then this one will represent our axial cracks. Okay, so yep, so that's one way to set up our weld probe with our Nortex 600. Okay, so next would be scanning the weld sample. Okay, so the weld sample that we have comes with 4 notches, 2 longitudinal and 2 axial. And you know that it's a common occurrence when we weld a sample, when we scan a weld sample, is that it will create drift on the impedance point due to the geometry. So however, with proper fine tuning, we will be able to minimize the drift and create a better scanning result. Okay, so again, oops, sorry. Okay, with the same setup, okay, we change the display to impedance. And then we try to scan both longitudinal defects on the weld sample. One would be on the toe of the weld and the other one on the weld face. Okay, so let's scan. So this is the longitudinal crack or notch on the toe. And then let's go to the weld face. And that would be the notch on the weld face. Okay, so you see there's a drift. So we can improve on this. So press freeze and then change your angle. Okay, so both of the notches or both of the display have on the same horizontal plane. And then reduce your horizontal gain so that both notches will be almost on the same vertical plane. And then increase your vertical gain to a required amplitude. Okay, so this one will be depending on the inspector. Okay, so try to scan again both defects and see if, yeah, we have improved the scanning. Okay, so first would be on the toe. So that's the notch on the toe, and then go to the defect on the weld face, and yeah, you can see that, yeah, there's no there's minimum drift. Okay, so with that, you can also add some persist erase so that it will not saturate your display. And you can use sweep and impedance for your display. And then we roughly scan the weld sample again. Okay, so first would be on the heat affected zone. Okay, we try to scan and see whether we can get the notch on the toe. So that's the one. Okay, so we just continue scanning roughly the weld sample. Next is scanning the weld face. So as you can see, there's a little drift, but you can still see the one of the actual defect. Okay, and now this is the longitudinal defect. After which you scan the other heat affected zone where there is a long actual defect, which so you can see on the display. So as we demonstrated here, that we were able to do a better scanning result when we properly tweak the parameters. Okay. And then last part of this presentation would be setting up the paint thickness probe. So provided the part you will inspect is painted, this will help you evaluate the paint thickness of the part. This will also roughly indicate how many shims you will use during the weld probe calibration. Okay, so with this paint probe, we will select a surface crack application. Okay. And then we will change the frequency to 10 kilohertz. Next is we need to disengage the alarm since we don't need it. After that, go to your display, change your grid to 10 by 10. And then change your horizontal position to 100. And then vertical position to 20%. Then after which you take your probe and put it on the reference standard. Press a long press on the null button to activate your automatic lift off. So this will automatically change the lift off of your probe. Okay. Then press freeze, change your angle. So it will be slightly above the horizontal line. Okay, once done, you can stack all the shims, 4 shims on top of the standard, and then put on the probe. And then reduce your gain until the impedance point reaches the first vertical line on the left part of the display. Okay, so once it reaches the first line, change your vertical position to 100. And then change back to 20. Okay, after this, you remove one of the shim. and then do it again. So change your vertical position to 100. And then put it back to 20%. Again, remove the shim. And then, of course, change again your vertical position to 100 and put it back to 20%. Then go with the last one. So just do the same. And then last would be the bare metal or the bare standard. So it should go to the initial null point. Okay. And after that, you can press your save with the long press and to create a reference display on your Nortec display here as shown. Okay, so that's the end of our presentation for Nortec 600 and Weld Kit. Back to you, Joshua.
Thank you, Franco. All right, I hope everybody can hear me because I apologize if just now there was some wind interference. So the next one, the next segment is the application of the Nortec 600 for tube testing. So heat exchangers and HVAC, which is heating, ventilation, and air conditioning systems, they are important components in nearly every type of facility. And these systems involve thermal energy exchange through many tubes. They undergo high pressure, they are exposed to dramatic temperature changes, and sometimes have corrosive materials flowing through or around them. So if unmonitored, these systems can fail and lead to significant potential downtime. So here are some of the common defects that can lead to system failure. Defects can be pitting, can be wear, erosion, corrosion, cracking. And these tubes are made of different materials and designs. For example, some are made of non-ferrous materials like aluminum, copper, and Marati brass, and some are of ferrous materials like carbon steel, and some also have fins, etc. Tube inspection generally makes use of techniques such as eddy current, remote view, near field, magnetic flux leakage, and ultrasonic for the inspection. These methods are typically only available in advanced testing equipments, which sometimes tend to be an overkill for example, small HVAC systems. So the Olympus Nortec 600 eddy current instrument can also be used for tube inspection and also presents a solution for your screening needs. The Nortec 600 offers the ability to perform eddy current, remote field, and near field methods. So let us take a look at how these methods are utilized. So as mentioned earlier, tubes can be made of non-ferrous materials. And normally, eddy current technique is the most suitable for such material types. Eddy current testing is quite sensitive to fine cracks, and it can also differentiate between OD and ID defects, which is outer diameter and inner diameter defects. Even defects under the tube support are detectable. It is also the fastest method of the three mentioned and can scan at speeds of up to 2 meters per second. The next one, if the tubes are made of ferromagnetic materials, then remote field testing will be a good solution. Remote field testing is sensitive to volumetric defects and for pitting detection. It is, however, slower than eddy current method. So for ferrous material tubes with fins, in the case of air fin coolers, near field testing is a practical solution. It provides excellent detection of ID defects and is fast and has simple data analysis. So let us now take a look at some video demonstrations by Franco on the various methods. But before that, let us have another poll question. Right. Thank you very much for your participation in the poll question. So Franco, over to you.
Okay, thanks, Joshua. So for this second part of this webinar, okay, I'll be using the Nortex 600 dual frequency and the HVAC heat exchanger tubing kit. Okay, so our HVAC heat exchanger kit comes with different adapters that cater to ECT, RFT, and NFT probes. It also comes with a 2-pedal foot switch for better workflow and a splitter to connect both probe and foot switch to the Nortex 600D. Okay. So this presentation consists of 4 videos. For the first part, I'll be showing you how to connect all these accessories and probe to the Nortex 600D. Second, I will set up the ECT probe. Okay. Third, we'll be recalling a saved RFT setup and scanning the calibration tube. Then lastly, we'll be recalling a saved NFT setup and scanning the calibration tube. Okay. So let's start with the by connecting the accessories to the Nortex 600D. So these steps can be in any order as long as the end result will be the same. Okay, first is plugging in your foot switch cable to the foot switch. Okay, and then the other end to the splitter. Then connect your splitter to the Nortex 600D. Okay, once you connected both, then you get the probe and then the corresponding adapter that you will use. For this one, we'll be doing the ECT first. So I'll be connecting my TA probe or bobbin probe to the adapter and then plugging the adapter to the splitter. Okay, so once plugged in, so you're good to go for your inspection. Okay, for the next presentation is setting up the Nortex 600D with the use of the ECT probe. So for this demonstration, I'll be using an Admiralty brass calibration tube with small defects and one internal groove. Okay, for this setup, we need to set the frequency 1, frequency 2, and mixed channel. And I'll be using the through hole and the support as my calibration points. Okay, so let's start. Okay, so for this same thing, I will choose the correct application. So this would be ECT pitting. Next is changing my frequency. So it will depend on the material that I'm using and the thickness. So this one I'll change to 8 kilohertz. Okay. Now I'll try to scan the hole of the calibration tube. Okay, so that's the hole. I'll press freeze and then try to adjust the angle until it reaches the 40-degree 40 degrees based on ASME standard. Okay. Then lower down my my gain until it reaches 6 divisions. Okay, so once set, I'll try to scan also the support, just making sure that the equipment is able to detect the support. Okay, so that's the support signal. Okay, so next is changing my channel to frequency 2. Okay, then going back to my main frequency 2 frequency, I'll change it to 4 or half of frequency 1. Again, I will scan the through hole of the calibration tube. So that's the hole. So similar to your frequency 1, I'll change the angle so I can reach 40 degrees based on the web grid, and change my gain until it reaches 6 divisions. Okay, next is scanning my support. So just making sure that the equipment can scan it. Okay, so that's the support signal. So next is changing my mix channel. Okay, so go to my display, changing my channel to mix. Okay, and then after which I will press the auto mix and try to scan the support. Okay, so the equipment will collect the data and will establish this as a support, and then it will eliminate it in the mix channel. So now I will try to scan the support again, and as you can see in the display, there's no signal already for the support. Okay, and next I will scan the hole, and that's my hole. And then same thing with frequency 1 and frequency 2. I'll try to change the angle and then the gain, so it will reach at least 6 divisions. So just making sure that your horizontal mix gain and vertical mix gain are equal. So this I need to tweak some more. So at least it will reach 6 divisions. Okay, so if you're satisfied, you can rescan everything again, support and the hole. So scanning the support, you can see there's no signal and you're only left with the hole. Okay, so once done, you can change your display mode to all-in-one. So you can have 3 signals at the same time. So from here, you can separate 3 signals by changing the positions. Okay, for my frequency 1, I'll change my horizontal position to 20. For my frequency 2, I'll change it to auto Y. And then change my vertical position, maybe around 20%. And then my mix, I'll just tweak it and change it to 80%. Okay, so now we can scan the support and the hole again. So that's the support and that's the hole. Okay, so you can see mixed channel, it doesn't show the support signal. So we'll try putting the support on top of the hole and let's scan again. So as you can see on the mixed channel, it only shows the hole. Okay, so now we can try scanning all of the defects, including the 10% internal groove. Support, that's your hole, and these are the remaining defects. And then one big indication that shows you the internal groove. Okay, so that's how to set up the eddy current probe with the Nortec 600. Okay. So next would be for the RFT. Okay. As I mentioned earlier, I'll just recall a save RFT setup and scan a carbon steel calibration tube with small defects. Okay, so as a limitation for RFT is that you will not be able to determine the defect whether it's found internally or externally. Okay, so it's unlike the ECT where any defect that is less than 40 degrees or below the hole is internal. We can see it as internal defect. If the defect is going outwards, so that means it's on the external part of the tube. Okay. So for this, we'll just select the correct application. So RFT pitting where? Oops, sorry. Okay, so after selecting the correct application, we will press the memory. Okay, and then just select the save application or file, which is the RFT differential. Okay, so similarly to your ECT, you can also show 3 displays or all-in-one display. Okay, and then yeah, you just try to scan everything, starting with the hole. So that's your hole signal. There's another defect. Okay, and then the last one would be your support signal. So as you can see on the mixed channel, there's no support signal indication. Okay, so that's the RFT video. So lastly, we will show you the NFT. Okay, so similar to your RFT, we will just recall a save NFT setup, and we will scan a thin carbon steel tube with internal corrosion and defects and small defects. Okay, so NFT is commonly used for detecting internal defects only. Okay, so whether it's in volumetric like corrosion and erosion or fittings. Okay, for Nortec 600, you have 2 options also for NFT. And at the same time, you need to select the correct adapter for this one. Okay, so let's go to the NFT. Okay, as you can see, we have a thin carbon steel tube. Okay, and for this one, we will choose the NFT erosion and corrosion application. Okay, so same thing as what I mentioned earlier. We just recall a save setup. Okay, and then you null your tube, your probe inside a good tube, and then yeah, you can see there's the corrosion indication, some fittings, and another corrosion indication. Okay, so the advantage of NFT is that yeah, analysis is quite easy. Okay, so you can see the difference between a good part or nominal thickness and then corrosion on the tube. Okay, so that's the end of the video presentation. So let's get back to Joshua for the summary.
Thank you, Franco. All right, so in summary, after you have watched the videos, all right, and the presentation. So the Nortex 600 itself, Olympus has combined its latest advancement with a high performance digital circuitry and eddy current flaw detection into one compact and durable portable unit. Its screen itself is crisp and vivid. It's about 5.7 inch. And also the Nortex 600 can produce highly visible and contrasting signals in any lighting condition. It is also lightweight and is powered by lithium-ion battery for up to 10 hours of standard operation. With a simple menu structure, the application menu which you saw earlier, the all-in-one display and real-time readings and signal calibration in freeze mode will help to ensure that inspections are quick and easy for any level of operator. So overall, it is a very good alternative solution for magnetic particle inspection as well as penetrant testing methods. Also, it is a good entry-level instrument for screening tubes. Effectively, you can inspect more with less. So before we wrap up, we would like to share a few answers to some of the questions we received during this webinar. All right. So let me just pick a few out, okay, because of time. So the first question is, can you scan parts with any type of coating using eddy current? So for this, it can, but only non-metallic coatings like paint. All right, metallic coatings itself will give false readings due to its conductivity properties. So another popular question, what is the smallest defect you can pick up in tubes? Franco, would you care to answer for this?
Okay. For the smallest defect, generally we would follow based on ASME code for the calibration tube requirements. So the calibration tube will allow you to know how small defects you are able to detect. And then we are able to pick up a small through hole with diameter of 1.3 mm on non-ferrous calibration tube of a diameter of 19.05 mm and wall thickness of 1.65. Okay, so yeah, I mean, basically it's based on the calibration tube requirements.
Thank you. All right, next question we have here is, what is the working temperature range for weld probes? So for weld probes itself, it comes with 3 categories and 3 temperature ranges. Normally, the standard weld probes can be used up to 150 degrees Celsius. And the long-wearing weld probes can be used up to 260 degrees Celsius. And high temperature weld probes can be used up to 399 degrees Celsius. All right.
Okay, I have a question here. What is the smallest defect the weld probe can detect? Weld probe can detect approximately 2 mm long defects. So this is based on the weld probe focus area, which is around 1.5 mm, plus the plus around 50% of that width. So yeah, approximately it's around 2 mm. Okay. Next one is, can we detect subsurface defects on carbon steel welds? Joshua, can you answer this?
Okay, sure. Subsurface. All right. Due to permeability of the material itself, so defects we can detect on carbon steel welds are normally surface types and very near to the surface only. All this is due to the permeability effects. All right. So I have here another question. Can we use other eddy current probes for welds? All right, so what we have here is actually the weld probe. So for other type of eddy current probes, generally the geometry of the weld will create unwanted signals and drift that will be difficult to adjust. So the weld probe is actually specially designed to help compensate this lift-off. Okay.
Okay, so I have a question here. Can we save acquired data in the Nortex 600? So unfortunately, no. However, we are able to save the screenshot and the setup of the of the of the screen by by pressing save button once. So after pressing the save button once, you can save both the screenshot and then the setup. So yeah, I mean, the screenshot, you will be able to use it on your report. And then of course the setup, when you want to do another inspection, you can just recall that setup that was saved. Okay. And then can we size defects in Nortex 600? It will still be based on your calibration tube, but ultimately it is just used as a screening device only. So it is not similar to our more high-end product for tube testing. Okay, so it will not really give you the direct reading in terms of angle and in terms of how much is the defect is, or in terms of percentage. So yeah, so it's just a screening device only.
All right. Okay, so I
Okay,
guess
wait. I think we still have. Okay. I have a question here from India. Is it? I'll just rephrase it. Is it able to adopt the Carto software? Unfortunately, no. Okay. So maybe during the mapping, you can use the Carto software, but during the inspection, it's kind of different. So you cannot really transfer the map or the drawing from Carto to your Nortec. So yeah, it's not possible. Then next, can separate ID and OD defects? Depends on the application that you're using. For eddy current, you can separate them. As I mentioned, if it's lesser than 40 degrees, you know that it's an internal defect. If it's more than 40 degrees, then yeah, it's an OD defect. Okay, but for RFT, you will not be able to distinguish the defects, whether it's internally or externally found. Okay, what else? How much fill factor is required? I think this is another question from India. So for ECT, it's around 85 to 90% fill factor. Okay. For RFT, it will depend on the we have this software that we will that guides us on the fill factor. So yeah, so basically for eddy current, it should be 85 to 90%.
Yep. Okay. So I guess this is all the questions that we have. Okay. So anyway, we hope that you have found this webinar informative and useful. So please also do follow us on the various social media platforms for more updates and news. And if, let's say, right now you don't have any questions, but later you have, just feel free to reach out to us, contact us through our website or anything, or even if you want to request for a demo, so do get in touch with us directly or through your local sales representative. So with that, we conclude today's webinar. We thank you again. Do take care, stay safe, and enjoy the rest of the day.